Okay, so chapter 11. Chapter 11 involves one thing, chi-square testing. Chi-square or squared. Sometimes it's chi-square, sometimes it's chi-squared. Chi, yep, it's a Greek letter. Okay, it's a Greek letter. It's this Greek letter right here. It's this X right here, this kind of cursive X. That's a Greek letter, pronounced chi. And then squared comes from the squared part. Okay, it's testing. So you know the parts of the test. That part hasn't changed. It's just a different test, but we still have hypothesis. We still have significance level. We still have assumptions. We still have test statistic. We still have conclusion calculations. We still have all of that because it's a test. It's just a different type of test. Okay. Today, all we're going to do is goodness of fit. These other ones, we're not worried about today. Okay. So just goodness of fit. That's all we're doing today. Later on in the chapter, we'll look at the others, but for today, just goodness of fit. Okay. Okay, chi-square goodness of fit. Why do we do a chi-squared goodness of fit? A goodness of fit test is used to determine whether a population has a certain hypothesized distribution. If we know what that distribution should look like or will look like, we use a goodness of fit. How good does the data fit the way they're supposed to? That's why it's called goodness of fit. Expressed as proportions of individuals in the population falling into various outcome categories. There are two types of goodness of fit tests. We're going to do both of them. The first one is equal proportions. Everything should happen equally. Everything should happen equally. All proportions are expected to be the same. That's the first one. The second one, there's a fixed or given proportions. Proportions are expected to follow given guidelines, given there's a way they're supposed to finish. Okay, that's the other one. We're going to do both of them. Hypothesis. The null will always be in words. Our hypothesis will always be in words. It's not going to be numbers. There's going to be no numbers for hypotheses on these. So you're going to say, you'll say the stated distribution of the categorical variables in the population of interest is correct. Something to that effect. The stated distribution of proportions is correct. Something along those lines. That's always going to be our null. Okay. The alternative would be no, it's not. Something is wrong with it. Something is wrong with it. They're not all equal, or they're not as given. Okay. All right. Our test statistic is right here. And it's also on your sheet, so you don't have to memorize it. It's not a very hard statistic. It's probably one of the easiest formulas we have. Okay. What does it mean? Well, observed, we take the observed, what actually happened, minus what we expect to happen, square that, and then divide it by what we expect to happen. Okay, so observed is the same thing as actual, what actually happened. Expected means what do we expect to happen? Okay, so what does a sigma mean? We talked about this before. What is that big E looking Greek letter? Summation, yeah, adding together. That's all it means, total, summation. Okay. Anytime you see that in math, it's just you're adding something up. Grand total, summation, which is a fancy word for grand total. Okay. All right. This is going to be the formula we use, which will also be the test statistic, and we'll use for our calculations. One of our conditions are going to be a little different. So we have to calculate what's called expected counts. Part of our formula says expected counts. So in order to use the formula, I need to calculate expected counts. How do I do that? One of two ways. The expected counts are all the same. The expected counts are all the same. They're all the same because they're expected to be the same. Or they're not the same, but they are found by multiplying the total of the counts by each given percentage. It's not that hard. It's not that hard to find. Well, and we're going to do it on the first problem. There are 3 conditions. The first one's always random. The second 2 are a little different. The second 2 are different than what we've been doing before. Okay? The independent, all expected counts are bigger than 5. Large counts, 80% of them are at least 1. Okay? And you can combine them together. You can actually combine these together. Because if all of them are at least 5, then 80% are at least 1. Okay? Degrees of freedom, n minus 1, where n is the total, is a number of outcome categories. Okay? However many categories there are. Okay, so, and then here's just the calculator, how to use the calculator. We'll go over that together today. Okay, so let's look at the first problem. First example. First example. Okay? Read the example. Read the example and tell me what you're missing. Okay, so after you read the problem, what are you missing? Numbers, yeah, where? Where should we have numbers? Well, we have numbers right here, right? 24, 20, 16. What type of numbers are you guys referring to? You guys are right, but be specific. What numbers do we not have that we need? Not the total. Not the we don't have expected and observed, right? To get expected, we need to use observed. Okay? So how can we get observed numbers? We need this. We're going to use, to find this, we're going to use this guy right here. But we need to find these guys, right? Or we need to know those guys. Okay? So, what does the question say? What are the questions? What does the question say? Or questions say? Okay, questions have question marks at the end. So the words before it are questions. So what are the questions say? Come on, guys. You guys know what you're doing. Please, yeah. That's why. Yeah. Otherwise I'll be talking to myself. I already know all this stuff. Okay, so what do the numbers mean? The numbers we do have, what do they mean? The company's claim, keep going. Yes. Okay. So the Mars Company. The Mars Company is the people who make M&Ms. They make M&Ms. Okay. They make M&Ms. They make a couple other things too. Candy, chocolate candies too. Okay. They say if you were to get every single M&M they've ever made, every single M&M, just regular M&Ms, not peanut, not in just regular M&Ms. If you were to get them all in one bowl or all in wherever, 24% of them would be blue. 20% of them would be orange. 16% would be green. 14% would be yellow. 13% would be red, and then 13% would be brown. That's what they say. Okay, that's their claim. What we're going to do is test that claim. We're going to test that claim to see if they're true, to see if we have enough information to say they're wrong, right? We're never going to say they're right, but we always say, do we have, or do we lack evidence to say they're incorrect? Okay. So we've done this before. We've actually done this problem before. But what does anyone remember what the difference was when we did that problem? Kinda. The way we did it back in the past is we picked one color. I think it was blue. And then we just tested that one claim. We just said blue. We're going to test blue. So I'm going to go through and count how many blues I have and see if it's 24% or higher or lower. And our null hypothesis was the proportion is 24%, and our is, I think, greater than or not equal to whatever we said. I can't remember what we said, right? We can do that already. It's called a one proportion test, one proportion z-test. We've done that. If you dig in your notes, we've done that. We did that. The difference with chi-squared is we can do all of the colors in one test. If we were to use chapter 9, I think, we would have to do one test, two tests, three tests, four tests, five tests, six tests. We'd have to do 6 different tests if we were to use chapter 9 skills to do that. We'd test blue first. Then we do another test. How many pages of tests do you think we'd have? Be pretty thick, right? Chi-squared says, no, you can do it all in one test. You can check each color in one test, right? We can check this claim right here in one test. We can check this claim in the same test. This one, this one, this one, and this one. That's what chi-squared allows you to do. So do we need to use chi-squared? No, but it's going to save our time, a lot of time, because I don't want to have to do 7 different one tests or one proportion z-tests. Okay, like we did in chapter 9. So like when we grade your FRQs, your practice FRQs, there's always different ways to do it. If you use a confidence interval, if you use a test, that's the thing here. Chi-squared just gives you a chance to do categorical tests. What do I mean by categorical tests? How do we know if it's a categorical test? We've done categorical tests already. How did we know they were categorical? These are each numbers, right? Aren't these numbers? But why are they categorical? What about percents make them categorical? They fit into a category, right? Right? Kind of like you guys said, like 3 or 4 things. If you put them all together, that's exactly why. They fit into categories, and each one has a percent that equals 100, right? These are all categorical, right? So we called those proportion tests, proportion intervals. We've done those, chapter 8, chapter 9, chapter 10, right? The thing about a chi-squared is it lets us do multiple tests at once, run multiple tests at once, okay? So the first thing we need to do is we need to find, so I'm gonna give you guys 2 of each. What I want you to do is write down how many you got. Write down how many you got. Okay, so open them up. You can eat them, but not yet. Okay? Or if you don't want them, you can throw them away later. We need numbers. We don't have numbers, so we need numbers. Okay? So, okay. Start with opening them up. Just put them on a paper. Don't put them on the table. Table's not clean. Just lay them all out so you can see every single one you got. First thing I need is a total number of M&Ms that we have. Okay, so that's the first thing I need. Put them both together. Put both packets together. So total, how many do you have? That's the first thing. Okay, so how many people have 10? Because there's a different amount. They say it's the same amount, but they give you different amounts in each. 11, 12, 13, 14, 15. Does anyone have less than 20? Does anyone have less than 25? How many do you have? 20. Perfect. Okay. Does anyone have less than 25? Okay. Does anyone have 26? 27? 28? 29? 29? Okay. 30s. Anyone have 30? 1, 2. So we got two 30s. 31. 1, 2, 3. Anyone that didn't raise their hand? I think we got, oh, 29. I got 29 right here. Okay. Okay, so what's the grand total? So change the 20 to a 30? Okay. So just give me a grand total. How many total do we have? 241. So we have, between the 8 of you guys, there's 241 total M&Ms. Okay, so now we need to figure out. So what you looking in front of you is your observed. That's your observed. Okay. So all of this is going to be out of so we need to count how many blues out of all of you guys. How many blues out of all of you guys? Okay. So put it on 2 hands, 1 hand. How many blues? How many blues? Okay, so I'm going to count this up. So keep them on 2 hands. How many blues you have? So I can see 7, 8, 10. Let's see, 7 plus 8 plus 10 plus 7 plus 8 plus 6 plus 6 plus 7. 1, 2, 3, 4, 5, 6, 7, 8. So total, there are 59 blues. Okay. Now oranges, count, same thing. Oranges, show me fingers for oranges. Oranges. Let's see, 8, 8, 7, 6. 11, okay. 7, 10, 9, and 9. Okay, so we have 65 oranges total. Greens. Now, figures for greens. How many greens do we have total? Greens. 4, let's see, 4, 8, plus 8. Okay, you guys are good. 2 plus 8 plus 7 plus 4, okay? We have 49 total greens. Yellows. How many yellows do we have? Yellows. Show me fingers. Yellows. 4, 3. Let's see. 4 plus 3 plus 2 plus 2. Okay, you guys are good. 1 and 1. So 2. So we have 13 yellows. All right, reds. Now reds. Reds. How many reds do we have? 2. Let's see. 1, 3, 6, 8. Plus 5 plus 1 plus 4 plus 2. Okay, we have 20 reds. And then last color, brown. Last color, brown. How many browns? 5, 10, 15, 25. Yes, 25. 25 plus 8 plus 3, 30, 36. 36 browns. Hopefully that makes 241. Nope, makes 242. Oh well. One of these is off. Okay, we'll go with it though. Okay, so that's our expected counts. So they'll always give you the observed, or you'll know how to find the observed. Okay, because observed is what actually happened. Now, expected. How do we know, or how do we figure out how many blues would we expect? How do we figure that out? There you go. Good. So we show one box. So we say 24% times, or 24.24 times the total, which was 241. Or let's say 242 just to make it even. 242, since they all added up to 242. So we multiply 0.24 times 242, and we get 58.08. That's how many we expected to get. Okay? So we're going to do that for the rest. You don't have to show the rest. You could just calculate the rest. So for orange, 20% times 242, 48.4. You guys can eat the M&Ms. We're done with the M&Ms. If you want to eat them, you can. If not, you don't have to.
You're deep. Look at this. What is this?
Okay. So we have our expected now. We have our expected. Our expected are right below. The next thing we're going to do is calculate chi-square. So when you do a chi-square, you kind of go backwards. We're going to do calculations first, and then we'll go back and do the rest, just because it's easier to do calculations first for chi-square. So chi-square says observed minus expected. Okay. So again, for one of them, I'm going to show, and then the rest I'm going to calculate on my own. So observed. So the observed for blue. The observed for blue was 59 minus what I expected, which was 58.08, squared, divided by expected. Okay, that's how I'm going to calculate it. So I'm going to go 59 minus 58.08, square that number, divide it by the expected, and you get a tiny decimal. I'll round it 4 places. I got 0.01457, so I'll round it to 0.0146. Okay, I want you to do that for the rest now. Do that for the rest. Do it for the rest of the colors. Chi-square. Don't forget to square before you divide. Okay, so when you get your answers, look at mine. I'm going to highlight them. So this is chi-square for each of them. We have 1 chi-square, 2 chi-square. All of these are chi-square statistics. Each of those are their own. The last thing we're going to do, the last part of the calculations, is adding all of those guys together. Adding each of those chi-square statistics together and getting one grand total. That's where the summation part comes in. So I got 26.1353. That's my chi-square. So my chi-square statistic, it's like a cursive X. Okay. Try to do a little, when you're writing it, try to do a cursive X. Don't do like a regular X because that's a variable. Chi-square, it's a letter, but it's not like an X. It's not an X. It's a chi. Okay. All right. So that's our test statistic. That's our z-score. That's our t-score. That's our p-value. Or actually, we're going to do p-value in a second. That score is going to determine whether we reject or fail to reject. Okay. Okay. So before we go on to the other parts, which colors, because this is a question they're going to ask. This is a question they ask a lot. Which colors contributed most to chi-square? Which colors contributed most to chi-square? Yeah, yellow. Why yellow? Because it has the highest number, right? What does that mean? Why is yellows so high compared to the rest? What is the difference about yellow that's different than the rest of the colors? There you go. The observed and the expected were so far apart that it creates a bigger chi-square, right? Almost half of our total chi-square comes from yellow, right? Almost half of our total chi-square comes from one color, right? The other one, 5.6934, orange, is due to the difference here. Which one has the lowest chi-square? Blue, yeah. Why is blue's the smallest chi-square? Exactly. They're expected and they're observed are pretty solid on, right? That's why it has the lowest. So if all of these, let's say all of the colors got pretty close to the expected, would we expect a high chi-square number or a low chi-square number? The lower the score, the lower the chi-square, the more likely that the observed and the expected were close. Okay? When we get high, big chi-squares, that's because of discrepancies between the observed and the expected. Okay? Okay. So we kind of did it backwards, the calculations. Actually, we didn't finish the calculations. I'll show you the calculation, finish the calculations in a second, but let's go on to the other parts. The other parts of a test, right? The other parts of a test that we always have. Okay. How many populations do we have? One, 6. Yeah, 6 populations. They're just different. They're broken up into color. They're all M&Ms, right? But they're different colors. These guys only talk about the blues. These guys only talk about the oranges. These guys only talk about the greens, and so on and so forth, right? So we have 6. So I don't want to have to write six of these. So let's figure out a way that I can not write it and put them all in one. So first of all, It's going to say the true proportion, but one for each color. Blue, orange, green. So what I'm going to do here is I'm going to put a B, O, G, yellow, red, brown. Okay. Show the true proportion, because it's a P. All chi-square will be true proportion because there are proportions. They're categorical. There's no means. There's no averages for chi-square. You could if you wanted to. I'm not going to, but you could. It's not. It won't be wrong. Okay. So the true proportion of what? Each of those P's is this, right? So the P for blue is 0.24. The P for orange is 0.20. The point P for green is 0.16, so on and so forth. So how do I write that in here? True proportion of the true proportion of colors of each color, sure. Each color of M&Ms in packets. Okay. Hypotheses. The thing about the hypotheses is it's going to be in words, but it's not very hard. So if you go back to the beginning, let's look at the statements I gave you. The stated distribution. The distribution is the table, right? The table. That's the distribution. Distribution means multiple things happening. Okay. So the stated distribution of the categorical variables or the proportions in the population is what? Not correct. That's how not how I would say it. How would we say it in this? What does it mean by it's correct? That's what I'm trying to get at. What is it trying to mean? What is correct in this? That by we don't want to say the company's claim is true. No. We want to say the stated distribution of population is as the company says. Right? Now we don't want to say it's true because we don't know that. But we just want to say is as stated, right? So the stated distribution of colors is as company claims. Okay. And then we could put, in other words, what does that mean? In other words, P P blue equals 0.24, P orange equals 0.20, etc. Okay. So what would our alternative hypothesis say? Exactly. It's not as the company claims. So it'd be the same thing. The stated distribution of colors is not as the company claims. That's all we put. is not as the company claims. So we don't care which one's off. Like, I don't really care if the blue is off or the orange is off or the green is off or the yellow or the red or brown. I don't care which one is off. I'm just saying it's one of them's off, because if one of them's off, that means another one has to be off to fill in for it. Okay, that's all I'm saying there. Okay, significance level, they didn't give us any, so we'll just use 5% as we always do. Okay. All right. What else are we missing? Okay, conditions, assumptions. Okay. So there are 3, but here's the thing about them. 2 of them we can lump into one. So the first one, SRS. So the first one is the first one. It's always going to be number 1. Doesn't matter what kind of test we're doing or interval we're doing. It's always going to be the first one, right? The data come from a well-designed random sample or randomized experiment. So when they talk about a random sample, what are they talking about in our case? In context of the problem we're doing right now. So how would we determine what is random about it? Like, what do you mean by random for our problem here? Yeah, it's kind of like a broad. I'm looking for something a little more specific. What can we put in there? That's what I'm looking for. What can we put in there? We're looking for some sort of system. That's what we're looking for. We're looking for some sort of system so that it's not biased, right? So what's one system we could do? Okay, so what would that mean though? Numbers in a hat. How many numbers will we have? What happens if I get one? Like, what does that mean? Like, numbers in a hat. Well, I don't know what to put in here. What do we put? That's what I'm asking. What do we put in here? It's blank right now. So what do we put? Well, what did we do? That's what I'm saying. What is that a random? Is that a system? No, that's not a system. No. Remember chapter 4? Chapter 4 dealt with all types of systems for simple random samples. Okay. What do we put here? I like how no one wants to make eye contact with me. I'm looking at people who are not making eye contact with me. That's the people I'm going to call on. Wow, I got 10 eyes on me now. Crazy. Crazy how that happens. What do we put here? Well, yeah, see, that's what I'm asking for. Where is the randomness? Is it how you pulled out each M&M? Or is it which bag you got? Or is it bigger than that? Like, where is the randomness? Or where does the randomness need to be? That's what I'm saying. Yeah, but they don't have a system. It's just however they come out of the machine, they put them in one and they move on. So they don't have a system of randomness. So what I mean, like, what do we need? Like, what I'm not saying there is randomness. I'm not even saying there is randomness that has been done. I'm not even saying we did randomness correctly. What I'm saying is, how in a perfect world, how would we do it? I'm telling you right now, there was no randomness done. There was zero randomness done. How should we have done it to pass this condition?
Assign a number to bag and use a random number generator to assign a bag to a person.
So bags like this, you're talking about?
Yeah.
Okay. So if I do that, only this bag can be chosen. Is this the only bag that was ever existed?
No. I
No.
don't think so.
No. Right? No, I don't have to do that. I don't have to do that. What else could I do? How do I get to this bag here? How do I get to this big bag in front of me? What's a system that would lead me to this bag here? What's a system that would lead me to that big bag there? Me walking into the store and saying, "Oh, this bag looks good." Is that a system? Because that's what I did. Right? That's not right. What would be a system that would lead me to that bag there? Okay, so maybe I'm not being correct. Maybe I'm not being specific enough. How could I say this differently? Because you say, "Oh, numbers in a hat." Okay, numbers in a hat, but that's not really. I mean, like, I don't see a number on here anywhere. So how would I know it leads me to this bag? That's what I'm saying. Like, you got to be specific, because this is what happens a lot of times, and students get docked on this all the time. I randomly am going to walk into a store and randomly do this. Well, randomly to me means that. Randomly to a statistician does not mean that, right? So randomness doesn't mean, it means the formal definition of randomness. You know what I mean? Because random, if you go ask someone after school and say, "What does random mean?" They'll be like, "Oh, just like a random person." That's not randomness, right? That's not randomness, because the only people that are around you after seventh block are the people in the 80s. What about the people way over there, right? You have no chance of picking them because they're not there. So how can we include them in our sample? That's what I'm talking about. Instead of people, think about bags. So I went to Target and went to go get that bag. How could I have done that randomly? Okay, so you're down here. Go up above, one step above. You guys are here. That's a good step. I like that here. Go a step above. Assign digits, however many targets there are within driving distance, Fresno and Clovis. 10, or not 10, 5, 6. I don't know how many targets there are. Randomly pick one of them. That's the first layer. Okay. Second layer was what you guys said. Go in, and if there's usually not many bags of these. At most, there's like 10 bags of these. Especially around time when there's not, when it's like Halloween time, there's tons of these. But right now it's not really where Halloween. So there was like 10 bags of these. So I walk in, assign a digit to each one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Somehow come to this bag. That would be a simple random sample. Why is that a simple random sample? Why is that fall under an SRS? Yes, but what? So why an SRS and not a different type of sample? Again, anything random, I have no control. So remember chapter 4. If we had time, I'd show you the chapter 4 notes. There's a lot of different systems. Why is this that one I just described you in SRS? Okay, so again, that's a randomness, right? Let's see. Again, that's part of randomness. Watch. Let me dig way deep. Every randomness, right? We did all of these. There's an SRS, there's a stratify, there's a cluster, there's a systematic, there's a multi-stage. What you guys are describing is all of these. I don't want all of them. I just want the top one. I just want that one. That's the only one I want. So what differentiates this guy? What I just did was this guy and nothing else. What differentiates that? Every single bag in all targets had a chance to be chosen. That's it. That's like me walking out here and picking someone. None of those people had a chance to be picked, right? That's what makes it an SRS. That's why it's just one of my pet peeves. Like people say it's random. Okay, which random? And you know what random means, right? A system. These are all systems right here. These are all systems, methods of doing that. Okay, so to do it, that's why I'm more detailed in this one than I have been in past, because we didn't have a system. There was no system there. I wanted you guys to explain what would be the good system to do that, right? What would you look for? Okay, I didn't do that. Literally, I just went into the closest target to me, grabbed the bag, walked out, and said, "That's it." You know, that's all I did, right? Exactly. It was extremely convenient, which is biased, filled with bias, right? So what I was trying to get at was, why is this? How would we do it in an SRS way? Right? You'd start at the top and then go from there. So that the bag I grabbed, because even if you go into like the closest target and you do your system of 10 and then you pick this bag here, well, what about the other bags in target? The other targets that you didn't go to? Those didn't even have a shot, right? You have to give everybody a shot. To be fair, you have to give everyone a shot. Like if I said I'm giving a prize to central students and only put you guys in the hat to pick, that's not a fair method, right? Everybody has to have a chance, right? That's what we're talking about here. Okay? Okay, so tomorrow we'll, like, exactly, we didn't do this. So we would highlight that. We're going to put that. I'm going to put that in. We did not do that. There was no randomness involved in picking the bags. Okay? And we're going to finish it tomorrow. All right. And then we'll do the other one and then we'll be done with goodness fit.